So moving to today's case, I would like to model a simple stent with a diameter of around 5 mm, length maybe 16. In the end, the pose dilatation should be around 6 mm, and the pressure that we use will be something between 11 and 16 bar. Divided by 10 will be around 1.1 or 1.6 megapascal. So let's move to the modeling side. I open Space Clean. Here I will go to the plan view and just go to the sketch tab. Draw a circle of 5 mm, and the thickness maximum thickness I would like to be maybe 0.2. This means 5.4 here. Let's go to 3D. We don't need this internal surface, but you can see here we have this outer surface. If I will click this edge and this edge, we can see that the thickness is 0.2. Let's pull a little this face, and we will go for 2 mm portion at this time. I also have some, of course I will not do such complex geometry today. I want you to see some inside thicknesses of the struts. So they range between 0.1 something and 0.192, yes, 0.14, 0.19. So let's create some windows inside this cylinder. I will click this axis, then go to Design Sketch Mode. I will click the plan view, and let's make a window here. I will offset on this edge, this axis, with 0.1. I cannot select this edge, so let's project it to our sketch, project to sketch. Let's offset it with 0.1. Yeah, I said that the window will be of 2 mm. This means 1 mm here offset, 1 mm here offset. Then useful for me is everything inside here. Then I can use a trim away operation, something like this. Yeah, this is the window that I need. Let's go to the 3D mode, and with this I will clicking no merge, I will just pull here and create a parallelepiped. I click no merge, so we don't have a single body, we have two separate bodies here. Let's create a circular pattern here. It says let's object to create a pattern. I need this parallelepiped and also a linear edge axis. Let's select the outer face of the cylinder, and it says, let's pull here, 7 bodies on the circle. Yeah, it says this. I'm curious about the remaining thickness that will be here. Let's check it. Let's do a Boolean operation. Combine, select a target, click a target object. Cylinder is a target. Then click the pattern bodies. It says click regions to remove. Inside there are some small red pink windows. So escape to get out from the command. Let's hide the pattern. I will click here, and we have some struts. If I'm checking for the distance here, we see that it's pretty big, 0.19. This means that the outside with control pressed, it's 0.37. It's pretty big. So what should we do? Maybe let's make the initial parallelepiped a little bigger, yes. So let's undo until we get to the initial parallelepiped. Ctrl Z, Ctrl Z, Ctrl, and we have this thing. So let's pull this here. .06 and here let's pull the same 0.06. I'll click no merge, then pull this here and repeat the pattern operation, circular pattern. Come on. We clicked. Click or select objects to... Okay, maybe I went too fast. Let's do the combine operation again. Cylinder is the target, then these are the cutters. Let's remove the remaining windows and hide the pattern. So here we have much smaller thickness. Instead it's kind of too small. Let's see this one, 0.24. I'm satisfied with this one. Let's increase here, yeah, instead of 0.05 let's make it, yeah, let's move a little. You know what, let's separate only this strut, okay, or small beam. Split body, I will split this body about this face, escape. Split body, I will split this body about this face. This means that all the struts are separate bodies now, yeah? Let's delete all of them, except one. I will click this edge and I would like to move it circularly, let's say. I have move, I will change the anchor or the reference for the movement to the axis. Then it will ask for an angle. 3.9, yeah, why not? And this, let's change again the reference and 1 degree. Let's verify the thickness now. 0.14, yeah, it's acceptable now. And let's pattern this strut, yes. So create a select objects to blah, axis. Let's select this face, and it remained with 7 instances, everything. Only these are, yeah, separate bodies. Let's delete the original parallelepipeds, and here I will unpattern, because the internal pattern relations are not useful for the moment. What I would like to do is to unite all of these bodies, yes. The easiest method would be to select all of them, but we can see that they did not unite here. Let's click here. Yeah, something occurred. This means that is this? Yeah, it's not useful. So let's do it proper and with no hurry method. We will click the select bodies to merge, then one by one, slowly with ease, we'll click all the objects needed. So even you can see here these are empty, so we can delete here and we're left with only one portion. So 12 millimeter will mean maybe around 60 instances or something like this. Let's there are many ways to multiply this portion. Let's firstly save this. Let me replace this. Okay. One of the options is select mirror plane, and this is the body to be created. I can also mirror again. I will select this face and mirror this part, and I have 1, 2, 3, 4 instances multiplied by 2 millimeter. Then I only need, I don't need to, let's not be picky. So having 8 instances, 1, 2, 3, 4, 5, 6, 7, 8, multiplied by 2, we have 16 millimeter, which is, yeah, in accordance with what we have here, 5 and 16. As, yeah, regarding length. Because this thickness is 0.1, let's make it 0.2, you see here, 0.1. I'll pull it with 0.1, 0.1. Let's see here what thickness we have, 0.2, alright, we are covered here. Yes. Let's save, and we're going to create now the blood vessel with the plaque. I select this edge, I'm going to the sketch mode, and here we have the plane view. Because we have 1, 2, 3, 4, 1, 2, 3, 4 windows, this means here we will have something like a symmetry. So I would like to isolate to show the axis, because I would like to create a plaque which is symmetrical to this axis, let's say, yes. So 3-point arc, we're going somewhere, let's not exactly touch this strut. And have something like this. What remains is to go here. So this is half of the plaque, let's say. Then the blood vessel would be something like, we'll offset here. This edge will offset with 0.01. Then we will extend this. Let's escape. Remember to hit escape to exit the command. I think we can move this a little outside. 7 mm would be nice. Yeah, you understand? So here is half of the plaque, and now we're going to obtain half of the blood vessel, let's say. Let's offset 0.2 thickness, yes, why not? And here we're going to close the blood vessel. Yeah, so we have half. Let's mirror everything in order to have the entire assembly. Mirror, it asks for a plane. Let's select an axis. Now we're going to select everything, and everything is mirrored. We have this plaque, the blood vessel. Let's go to 3D. Then we will execute a Revolve command. You can click the unneeded line, delete. Yes, pull. We have the Revolve option. It says select an axis to rotate. This is a good axis. Select faces or edges to revolve. This is a good face to revolve, also this one. And we will write from the keyboard 360. If you want to understand what occurred, you select the axis, then go to section mode, and you can see here what occurred. Yes, a small gap here. Ignore these artifacts, graphical errors, and here a much bigger gap. Let's say I'd like this to be even smaller. Let's see if we can. So if I select this edge, it will be the outer edge of the plaque. Instead of 5.31, I'll write 5.32. Let's see what. Because I forgot to hit no merge here. Yeah, so at this moment this software does not think very well. Let's decrease the thickness. Instead of 6.1, can we do, I don't know, 6.08? Can I? No, of course I can't. Why should it be possible? No problem. Let's triple click the blood vessel. We also have this option to make it transparent, and we can see here what's happening. So this is the geometry part. We will move to the simulation part in the next step. Let's save. So what we can see is that the stent somehow united with the plaque, so we need to separate them. Let's right click the vessel, hide. Then we have this option, split body. Click a target object, of course this body. Then we have the cylindrical face, which is somehow interrupted by the plaque here. Let's see if we can separate. I will hide this stent in order to see what occurred here. The stent now is somehow imprinted on the plaque. Let's select all these faces and just hit the delete button. Everything is round now. Let's also look now on the stent, what occurred on the exterior side. You see, we only gained this face. I think it was stolen from the plaque. Let's select all these extra additional faces with Ctrl pressed and hit delete. See if we are in luck. We are not in luck. Yeah, alright, let's separate them. Yeah. Nope. Alright, let's delete all of this. Why should it work? Well, it's possible also not to work. Let's at least make this plane. Let's materialize this plane. So I created the midplane of the stent. Now I can firstly split this body, and I would like furthermore for this plane to move it, to copy it, yes, with Ctrl pressed. I will copy it here with 2 mm. Then I will split again this stent with this plane. I will delete this part. I will mirror what we have here. In here we need to insert this, not this, but two of these. Yeah, let's see. So I will copy again this to 4 mm. For fun, let's split this body with this plane. I have this thing which I like very much. Then you know what? Let's just copy paste. Move this object, the last one, this one. I'll move it on this direction. Oh, it's dependent on the other side. Alright, I will triple click 1, 2, 3. Right click, make independent does not work. You see why? Maybe some time ago I said that I don't like having mirroring relationships and pattern relationships because they tend to stay. Right click, I'm looking for make independent. If someone sees this, of course it's not possible. 1, 2, 3. Make independent does not work. Alright. Let's see if I can hit a mirror. Mirror this part here. Yeah, it's nice. Let's repeat the mirror. Mirror according to this. Only. It doesn't mirror once, it mirrors more. Because it merged here. Let's uncheck the merge thing. Mirror this. Don't merge, don't create mirror relationships. Yes. Mirror with these faces, don't merge, don't create. Yep. And now let's unite everything because we have several separate parts. Combine this part with this part, Ctrl pressed, with this part, with this part, with this part. Yes, now we have a nice stent. Only what we will need to do is that the outer face, let's decrease its diameter a little more. So instead of having 2.7, let's have 2.68. In order to decrease the gap between the stent and the plaque. Show wall. We're going in section view and we're looking here. So the gap is not the gap, this gap is more pronounced, let's say. Let's leave it like that. Yes, we have 3 parts, 1, 2, 3. right click source internalize all. This is a very good command if we're using external parts or maybe borrowed, copied parts from other with other provenance. Let's save. Yeah, and I think that's all regarding the geometry. Now that we have the geometry made, let's perform the structure simulations. We'll drag and drop a static structural simulation, then import the geometry. Now we're going to create the proper materials. For the stent, we'll choose a non-linearly defined steel. So let's go to engineering data sources and access general non-linear materials. We're going to select structural steel. Let's say stainless steel, why not? We press again engineering data sources to go back to our favorite materials. So let's delete firstly this one, and we're going to modify this one as follows. Let's increase the density a little. Here we need to have megapascals, 210. 0.3 Poisson ratio, and here when we introduce plasticity, let's make this one, instead of 18, let's make it 800 megapascal. So this is the material for the stent. Let's let's duplicate it and create the material for the blood vessel. We don't know now which one is it, artery, vein, capillary. We are not, it's not important for the moment. So let's define here 1000 kilogram per cubic meter. Young modulus 0.5, Poisson ratio 0.475. Let's delete bilinear isotropic hardening because we don't take into account plasticity here. In a way, this is kind of a simply defined hyperelastic model, let's say. Let's duplicate this and create the Plaque material. Density, let's make it a little less. Let's make it even softer, and we leave this the same. Alright, so we have the materials defined, and we go back to the main window. So let's double click the model cell in order to insert the pre-processing details. I'll minimize this window for the moment. This is what just opened. No, not so much. So this just opened. So firstly, let's name the parts as needed. This is the vessel. Inside we have the plaque and also the stent. Let's assign the proper materials. So we assign the vessel material. This is a well-known bug here, so we need to go to materials. Let's select the vessel. Just make sure that this very intense green is shown for assignment. So select the vessel, then go to vessel here, right click, create material assignment. Now when it became red, we know that the proper material is here. So let's repeat. Plaque, click plaque, right click here on the plaque material, create material assignment, and you can see that the plaque is assigned. So click the stent, right click here, stainless steel, nonlinear, create material assignment. Alright, we have the materials defined. Let's go for coordinate systems. I will create a new one. Click the outer face of the blood vessel and change its type from Cartesian to cylindrical. We kind of need to have a radial displacement, let's say, so the rotation should not be as shown here, but should be, let's say, on the plane XZ that we have now. The easiest way is to assign the Z-axis aligning to Y absolute axis. So let's go here from the relative Z-axis and align it to global Y-axis. So you see we have the proper rotation because we need to define the displacement about the X-axis, which is in reality all the X-axis from this rotation plane, from the, let's say, XY plane, let's say. So all this being done, let's go to contacts. We can right click each contact and choose rename based on definition. Regarding vessel to plaque, we have nothing to comment, we can leave it like that. But regarding plaque to stent, let's change its properties to, instead of bonded, to frictionless. And it's very easy if we choose just a touch. Everything should be taken care. Let's save this project. A few days have passed, so we'll write here 24. Minimize, and we're back here. So regarding the mesh, let's assign an element size on the plaque underneath inside the blood vessel. Now let's ensure that this vessel will not be modeled with hexahedrons. So method tetrahedrons. It's sinusizing for the vessel 0.5, let's say, and a sphere of influence. Yeah. So when the stent will expand, will push, let's say, the plaque on the periphery, let's say, outside. So we need to somehow refine this this region, the contact region between the stent and the plaque, when the plaque will be deformed, also when the stent will be deformed. So the easiest way is to just select both bodies with Ctrl pressed, apply, and instead of element size, choose here a sphere of influence, choose the coordinate system that we just created. You remember this one? Let's insert a radius of 4.2, and here, yeah, 0.21. Let's make a section view in order for you to clearly see what we encompass here. Yes, so these three struts, let's say, will be finer when touching this region of the plaque. Let's just right click and generate mesh. So coarser and finer here, coarser and finer. Alright, so we can minimize on these. Let's go to analysis settings and choose the solver type direct, large deflection on, auto time stepping defined by should be on, defined by substeps, let's say 10, 5 and 200. And you can extrapolate if, let's say, if there will be a physical time and we have 1 second, the duration of the simulation, let's say, then when divided by 10 we have 0.1 as a time step, let's say, then 0.2, then 1 divided by 200, we have, let's say, like a minimum time step, 0.005 seconds if we are judging from a time perspective. But this analysis does not take place in time, it's not dynamic, so it's purely static, let's say. This is why we are using substeps. What we want more is here on the output controls. Let's make everything yes here, because we will be interested in getting also other output. Let's minimize here. We're interested in the force reaction inside between these parts, so this is why we made everything yes here. So let's apply the boundary conditions. I will come back a little to this image and remind you that when we have a stent diameter of, let's say, 5, the maximum post dilatation should be 6. We have here another hint, instead of 5, maybe 5.5, let's say, and we need to judge like this the dilatation. Let's make a small screenshot here, only these two, alright, because I want to draw here. So when we say 5 on a diameter, this means that on the radius level we will have 0.5. I meant 6. So from diameter 5 to diameter 6, this means that we will gain 0.5 on the radius. Yeah, because if we have such a circle with phi5, then we have another bigger circle, yeah, with physics. What I mean is that we will have such, yeah, two small gaps, let's say 0.5 here and also 0.5 here. Yeah, if we're drawing a line passing the circle, yes, on the diameter, this is the center, let's say. So 0.5 here plus 5 plus 0.5 will equal the 6 here. This is how I'm judging, yes. And here it shows that if we are going to apply a pressure of, let's say, 16 bar, which is 1.6 megapascal, then we're going to have a, let's say, 0.5 dilation, total dilation, yes, which will split on the radius exactly as here, only half of those dimensions, 0.25, 0.25. Yes, so because the circle is not phi, yeah, phi6 is written here, estimated here, the circle is phi 5.5, let's say, approximately, and these gaps will be lower. Instead of 0.5, they will be 0.25 on this particular table, let's say, with the compliance. So this is why I'm justifying what I will do next. I will choose a value between 0.5 and 0.25. Yeah, and this value in my case will be 0.35. I want to push a little the scenario to make it, let's say, kind of a worst case scenario or something like this. Let's go back to the simulation. So let's apply this displacement. On the inner face of the stent. By the way, if you have bodies that kind of impede your vision, you can just press F9, well, or right click hide face. I want to hide the body F9, yes. So we're interested in the F9 to hide also that it does not work. Why should it work? You can get out of the section plane, just uncheck here. Oh, so I unchecked the section view and it doesn't show. Yeah, let's add another bug to the list. So we were on the displacement load. I wanted to show that is you can see that is applied also on the invisible side of the stent. So it's a full cylindrical shape, let's say. And when we're choosing here the coordinate system that we just created, you can see that we can apply this radial displacement, yeah, about z-axis, about x-axis, I'm sorry. Z is along the length of the stent, or yeah, along its revolute axis, let's say, and x is the periphery. We have in this plane xy, we have an infinity of x-axis. So let's assign here 0.35, which is between 0.25 and 0.5, as I have shown earlier. We'll let the y component free, and we will make the z component, let's restrain it a little more. We will make it 0 to help the solving. So we will not allow, let's say, a shortening of the stent at this moment. We want to help the solving. So another displacement will be sort of like shovel bodies. Let's somehow fixate the extremities, the sides of these of the vessel and the stent. So it's very easy to just select these let's say lateral faces with Control pressed. I'm talking about the blood vessel and the stent. Apply. Let's select here coordinate system. We will leave the radial component free, then the y and z will make them 0. Yeah, somehow we will not allow shortening, and we will not allow, let's say, rotation of these two bodies. We will not allow the rotation about the y-axis. When we apply more and more boundary conditions, we kind of give we remove the unknowns in the finite element equations, and this means that we help the solver solve the FEA much faster. So these are the boundary conditions. Let's ask for some outputs. During the solution or the solving, I'm interested in seeing the deformation and the stress. Right click, switch to automotive mode, and here let's go for the classical total for misses, and we're going to insert a force reaction in the contact region. I'm talking about between plaque and stent. Yes. If we were not to make here everything yes, we could have not chosen, or we couldn't find out the force reaction in the contact region. So let's save now. We're going to assign here, remember to use the number of physical cores that you have available. Just Ctrl+Alt+Del, go to Task Manager, Performance, right click, change graph to logical processors, and you can assign something very close to your physical cores. If you don't do CFD, avoid the logical processors, so when performing fluid dynamics you can go and use the logical processor. Just when performing structural and explicit, go for the physical cores. So let's go close to what we have. Maybe 50 is enough. Solve. And we're going to look inside. When you have such a error exactly from the start, you need to just clear generated data and again and again try to solve it. Yeah, thank you ANSYS for these bugs. With a little patience, we can start the FEA. So when we get such a warning, this means that the FEA started. Looking on the solver output, we see some initial, let's say, log and details. We're interested in the force convergence plot. Let's see how it works. You can also check how your cores are loaded if you come up with the task manager, and yes, you can look and you can count all the logical processor and see that they are loaded according to what you prescribed here. So I'll interrupt it for a while until we get advancement on the solving. Such a red line during the solving means that a bisection occurred, which usually says that the time increment has decreased accordingly. So you can see here it started with 0.1, then it decreased to 0.035. You know, all these let's say time steps, which in reality they are something like sub steps, they will take values according to what we prescribed here. So it started with 0.1. I'm talking about when you divide 1 with 10, 0.1. Then it can go as low as what we divided here, if you remember, 0.005. So if we're going to look on the time increment, it can go to 5e minus 3. So we're on the right track, I would say. Let's go to the fact that it doesn't decrease anymore. This means that it found the proper convergence. Also, when the time increment is increased, then we have a nice convergence, which can be visualized by clicking on forced convergence here. Look here, stop step, or let's say something like time step. Yeah, you can equate these two terms. the converged. This is the what we're looking for, the force criterion to be, let's say, below for the force criterion, which is this kind of green line, to be above the force convergence line. So, and you remember the end time, let's say, is around 1 second, and we are already approaching the half of this solving. If the graph gets too cluttered, yes, and you can let's say make it coarse or rarefy it by choosing here, instead of showing all display points, maybe show the last 10 points, and we have a, let's say, much decent view over the force convergence plots. I will pause and then go back to the final steps. So we're approaching the end of the solving. Remember to save often. We can minimize here. Let's assign more items. A directional would be interesting, and instead of the global coordinate system, let's choose the system that we created and choose this direction, the X. It is already here. Alright, then let's go for an elastic strain. I'm interested in also an elastic strain only in the so-called hyperelastic bodies, and I also want to see the stress only in these two bodies with control pressed, stress equivalent from misses. From the toolbox you have also contact tool. Yeah, let's leave the bonnet for a while. We can insert pressure, then penetration item. Then we can go to the worksheet button and here ask for more if we like to see, let's say, some vectors. And what would be interesting here? One of these two. Let's see which one applies, because we have a static simulation, and I think the kinetic energy cannot be shown, of course. Right click, create user defined result. So here, right click, evaluate all results. Save. Let's look a little on the total deformation. Here the scale is not correct, so let's go to one scale. Let's animate a little, 50 frames. You can hide the edges of the mesh. Alright, and in the section view things will look much more, let's say, correct and easy to understand. If we want to see the correct radial displacement, let's say, we need to access this directional deformation that we created about the coordinate system. So yeah, it's pretty similar to the other one. It's kind of logic because we apply 0.35 and yeah, it's normal for this value to be my maximum 0.35. We just wanted to be sure. Alright, let's look a little on the equivalent stress. You can see that the values are pretty high because we exceeded what was recommended. Remember that I made a judgment here with 0.25 and 0.5. Yeah, it's kind of close to plasticity. But when using a superelastic null, plasticity should not occur. Let's see, just for fun, if we have plasticity, of course, inside the stent. Let's click the stent. All bodies evaluate our results. Yes, we have plasticity. So this is why I'm sure if we are going to change here from 0.35 to 0.25, I'm sure that the values would be much smaller. I will do this in the next FEA. Let's look a little on the strain on all parts, strain only on the hyperelastic parts. Yeah, the specific deformation. You can check the fact that there is no penetration collision. If you show also the element edges, yeah, and you can see that they do not interfere or collide, so they are clearly separated during the FEA. Everything done because we chose just to touch in the contact definition between the stent and the plaque. Let me remind it to you. It's very important. Please note down and remember about these options. This option. Geometry modification interface treatment, just attach this will save you from lots of trouble and it will kind of solve everything correctly in most of the cases. We've seen stress, strain, everything. Let's look a little on the force reaction between the stent and the plaque. Let's hide a little the elements. Maybe 40 frames to be faster. So this is the force reaction. Let's see some values. pretty small values, considering the fact that we have one of the sides is much softer, let's say. Why is this useful? If we're going to find out exactly the surface that gets into contact, yes, let's draw a little. What gets into contact, exactly we have only such faces, and continued on the entire circle. Here and maybe here we have and continued on the, yeah, also here, also here, also here, all these small windows. I will make also a hatch for you to quickly understand what I'm doing here. If we were to, let's hatch now, to obtain the proper contact area between the stent and the plaque, the area of the hatched surface, yeah, in reality the area of the small struts that come into contact, so this area, yeah, can be used in, you remember the formula for the pressure or the stress, force over area. So we have the force reaction, this is force reaction, so we know F, yeah, we know A, we know F, this means that we can find the, let's say, the pressure, or sigma normally is for stress, it's kind of internal pressure, yeah, so you can somehow make a judgment here, let's say 1.8 E minus 5 Newton over the area. This is pretty interesting. Let me show you how to find out this area somehow. So let's get rid of the section view. What do we know? It worked now. Let's hide some of the parts. Select mode. Can I select them? Of course not. So I will. Let's hide what we don't need. Then if we select the outer of the stent, outer face of the stent, we have here the selection information button, and we can see that the surface area is 53. I lost the previous calculation. Let's make another one. What I want you to understand is the fact that in, let's say, in pure contact, we have only one strut, let's say. Yes, so let's use this. Maybe change the color to something much visible. Yellow, yes. So you remember I had the area of the entire stent, the outer area was 54. Instead of thick, let's go here at medium, round, alright. So 54 square millimeter was the entire area, but we have only one strut. How many struts do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And we also need to take into account that we have these struts. 1, 2, 3, 4. Yeah, how much do we have? How many? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, maybe also 9. So this means that we should divide this area maybe much stronger. Let's say maybe around 12, give or less, give or take. 54 divided by 12 is around 4.5 square millimeter. So now you remember, let's go to the force reaction. What I forgot here is the fact that it shouldn't be on global coordinate system, it should be with the coordinate system. Result selection, let's choose only the x-axis to have only the, let's say, the radial component. Right click, evaluate all results. Now we have a proper force reaction. Look here, 0.5. So this is the proper area. The force reaction is this one. So if we are going to use this in a formula which somehow is the pressure, then we have, let's say, 0.55 over 4.5, which is, let's say, around 1, I think. .12, yes, 0.12 megapascal, by the way. Yes, so this value needs to be compared with these values, yeah. So if we have around, you remember, so let's say pressure from compliance is, I don't know, maybe 1.5 megapascal. We should get from the FEA a value that correlates with this one. This means maybe what I divided here was a little too harsh. Yes, and if we are going to divide, I don't know, let's say with 8, yeah, I'll open a Word file here just to be able to draw. So pressure from compliance is given by, let's see, something like this, 16, approximately 16 bar, which is, I want to remind you, approximately 1.6 megapascals. And in order to make a correct correlation, let's change the displacement. Instead of 0.35, let's make it with to 0.23 as prescribed here. So this should mean that is applied to, let's say, radial displacement, displacement air from radial 0.23. yeah, instead what we have now, we have 0.35 millimeter, yeah. So the first step would be, let's remake the FEA with 0.25. We close this one. And we're going to duplicate it. And here on the setup cell, right click, rename 0.35 millimeter displacement, and here let's just copy paste 0.23, I said, millimeter displacement. Let's repeat the FEA. I want to have a, let's say, good correlation. This is why I'm remaking this FEA, in order for you to understand the influence of the pressure and of the displacement of the radius and everything. So this one maybe 0.23, save and solve. I will return when the FEA is finished. So the FEA just finished solving. Let's see. So we're going to check the radial displacement. Of course, as we applied, as we prescribed 0.23, it is given here. The strain is much less. Let's look on the plastic. Strain on the stent is, it has lower values. Now on the force reaction, so it's 0.3 now, yes. So we have a force reaction of exactly 0.3. Let's somehow calculate the real area in contact, let's say. So this portion, yes, strut with these other struts, they constitute a portion of the entire stent. So let's say if we have such instances in the entire stent, let me draw again. So the entire stent consists, seen from here, let's say, the entire stent consists of such multiple instances, I'm drawing them separately in order to understand what occurs here. Let's say, give or take, what is in contact is only such a portion, yeah, such a portion, and we have, let's see if we can, yeah, we have in the entire stent, we have in section, or how to do it, let's hide the vessel and the plaque. So we have, this is an instance of real contact, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say 9 instances, even though we're missing here and here. I will say 8.5, yes. You remember the surface. The entire surface is 54. So we have, as a surface, we have 54 square millimeter divided by, I said instead of 9 instances, maybe 8.5, which equals 54 divided by 8.5, 6.35. So having these two, we can find pressure . Yeah, which is 0.04 megapascals. This value needs to somehow be compared with this value, and yeah, the results are not nearly close. So this value 0.04 megapascal can be seen on the, yeah, it's close to what we have here, contact pressure around 0.04. So our judgment is, let's say, correct. Only we don't have a, let's say, a proper correlation with this. These 1.6 megapascals from the inflation pressure.